Hey guys, I'm back, and this is Academia on Demand, and I am Josh Myers, and I am bringing you more of applying bonding theories and the idea of using these theories in order to solve problems in the classroom. So what we did in the last video is we talked a lot about the similar bonding behaviors. So similar bonding behaviors of elements in the same group, and we used the example of sulfur and oxygen, same group. And this is because their hybridized orbitals are the same when they bond in molecules, because they have the same number of valence electrons in their outer energy level. And then we talked about bonding using the extended octet, the empty d orbital, extended octet bonding, And now, what we will be talking about today, and talking about in this video, it's the same day, I promise, I am just keep on rolling with these videos, is delocalization. Delocalization, and how this big idea, which will be the subject of this video essentially, delocalization, how it can be explained through, most importantly, hybridization. Because as we know, we've talked about this idea in Lewis theory context, in which we would say there's no more energetically favorable, more is a very important word here, more energetically favorable state of bonding. Energetically favorable state. But as we will discover in this video, we know science is all about discovery, that there is more to it than this simple explanation. That there is a large explanation that has to do with hybridization and the idea of pi and sigma bonds. Because we actually in the last video left out the idea of pi and sigma bonds in the molecules we were drawing, because I was always drawing molecules that only had sigma bonds in them, or only electrons in them that were hybridized. There were no double bonds or triple bonds that would signify pi bonds or pi electrons. And we will talk more about pi electrons in this video. I was saving it. And so you're probably wondering exactly, if you haven't seen the previous video, why this line up top here is drawn out. Why this line up top is drawn out. And we'll see if we can keep this separate. And this will be our question answering area. Okay, so, and it says using bonding theories in order to, and I said in the previous video, explain the bonding of, and now here in this video we will be explaining the bonding using these bonding theories of O3 C6H6, and then if we have time, because I don't want to make this one like the last video, we might go into another video with a special case of NO2. We've also talked about this molecule before, but it gets really interesting once we start talking about it in terms of hybridization. Okay, so our first molecule that we have to explain, and we'll see, maybe we can leave these up here. If we can, this will be our space. Hopefully we can do it. We are going to be talking about ozone. So, ozone, I always like to write out the proper name of the element, or compound in this case, so we can really get a practice with this, because I haven't done any videos on it. So, ozone has 3 oxygens. This means it has 18 electrons in total. 18 electrons in total. And so if we draw out this molecule from memory in the previous videos in which I've discussed it, we know that this molecule has the Lewis structure of the central oxygen with the lone pair, and then the oxygens over here that have 2 lone pairs, and but then finally, to complete the energetic stability so that the central atom has 8 electrons, there is delocalization that occurs. And as we've talked about before, the reason for this is because if we were to put electrons here, if we were to put 3 lone pairs on each oxygen, even though we'll see a little bit later that this isn't at all accurate to what could possibly happen, if we put another lone pair on each oxygen, we could put these oxygens, we could potentially make a double bond here, and there'd be 18 electrons. It would perfectly fit this idea, but the problem is, even within the idea that there is an extra lone pair on each of these oxygens, which we know isn't true, even within that idea, there is no more energetically favorable state, because as we know, both bonds correspond to the same delta En, the same change or difference in electronegativity between these two bonding species. So therefore, neither bond would result in more energetic stability over the other. And so what ends up happening is these electrons that would be the lone pairs, theoretically, if we were thinking about it that way still, they all just come into this middle and become in a superposition. They become delocalized. I'm going to write this superposition word because it is physics, and physics is interesting and very closely tied with chemistry, especially when you get down to the deeper quantum levels. Okay, and so what does this delocalization represent? And I'm going over this because we really want to be able to understand what this is, so then when I explain it to you exactly how these things are really happening, we can kind of be at ease that we understand the concept of this delocalization. So this delocalization, because as we know there were two lone pairs here that we threw into the middle here, and these dotted lines somehow represent these electrons, which there are 4 electrons, spiraling in this continuous path, this somewhere in here, this path between these two extreme bonding states. And so between the two extreme bonding states, where there could be a double bond here or a double bond here, as we discussed before, these 4 electrons travel in between. They are located somewhere in between. From a probability function point of view, they are somewhere in between these 2 oxygens, these 2 potential bonds, the double there or the double there. So how does this idea happen? How does this idea where this stuff happens, where these 2 electrons from each, that isn't actually what happens, but how do these 4 electrons come to be in this superposition state where it makes the entire molecule more energetically stable? And that is what we will explain here, in which case we will draw out we will label this oxygen star, and this oxygen triangle, because they are the same. They have the same hybridization. They are in the same situation. So the oxygen star, we're talking about hybridization. We can actually maybe just skip right to the hybridization. Actually, no, let's not skip it. Let's do it all out, because this is important. So this oxygen, as we know, it has its 2s and its 2p. Okay. And it has its full and then its 2 half full 2p orbitals. Okay, so that is the electron makeup of the star oxygen, and when this electron is promoted, it will have this electron, it will have that electron configuration in which it will be the new hybrid orbital will be, oh no, I have to make this better. I am very bad at drawing these. They're very simple, Josh. You should be rocking and rolling if you understand supposedly so much about chemistry. It's debatable, I guess. Okay, so we've got our hybrid orbitals, we've got our s, half full, and then our p's, which are full, full, half full. Okay, so if we take this structure to be accepted, because as we know, this is the structure of ozone, this central oxygen, which is the star oxygen, it's bonded to two things. This satisfies this s orbital and this p orbital, who are looking for another electron, a partner, to satisfy this orbital completely. And then it has these two full electron hybrid orbitals. And so we can easily connect at least one of them to this lone pair. This is very easy to do. But where does this one go? This is where it starts to get mysterious. And this is where I'm going to start drawing an alternative picture of how this would be created. And so we've got this oxygen, this star oxygen, and it's got its lone pair right here. Let's pretend it has both lone pairs just for a second. Even though we know this is the proper structure, let's pretend for a second that it has both its lone pairs, as its hybridization here would suggest, given its two full p hybrid orbitals, and then it has its bonds with these oxygens. And as we know, these oxygens, when hybridized, actually have the exact same structure. They have the exact same structure when sp3 hybridized. So they would have the structure of the bonded pair. So this s orbital would actually match up with the s orbital of the star. So it would create this bond and this bond because they are the same. And then we would have these two lone pairs, and then we would have this p orbital that would be sitting all by itself. And this would represent 18 electrons. Everything would be good. But we know that these oxygens cannot possibly be energetically stable the way they are. That just does not make sense that they could have just one oxygen in their hybrid orbitals and this would be the most stable state. The problem is that if you look back at this p orbital that we don't see here, this hybrid orbital is full, which means that we cannot even theoretically have another bond here. This is not possible because the other orbital that these electrons, this one electron, this half-filled orbital, it's right here, would bond to, it is a full orbital. So how can we get around this? This is a big problem because we cannot have a molecule that looks like this. This is a massive problem. So how is it solved? And this is where we need to use our imaginations a little bit when we are perceiving these molecules in our own heads. So what if, and we're looking at delocalization here, what if this p orbital could be split into two half orbitals that are half full? If this could be split, let's draw a better arrow. I keep using my finger and it is starting to get very blue. Okay, so in these orbitals are, let's just draw boxes, half orbital, because we split the full orbital in half p. Okay, and so if we split the orbital in half, this would seem to work perfectly. This would work very, very nicely in bonding with these two these two single electrons right here, because they could go here and here. But now the issue is if both of these things happened, we would have the potential for as many as 5 areas of electron density around this, or sorry, 5 bonded and non-bonded pairs around this oxygen. We would have this non-bonded pair and then a double bond here and a double bond here. But is it really a double bond if we were thinking about it in that context? Because if we were thinking about it in terms of half orbitals, that are full, if we were just pretending for a second that these half orbitals could possess 2 electrons, we would say 1, 2, 3, and then 3.5 with this like half orbital double bond, and then 4 with this other half orbital double bond. And this would create this idea of having these 4 electrons. This idea of splitting this full hybrid orbital in order to bond with these single electrons. And now this is really the critical point where this really seems to make sense. Really seems to make sense, and this is how, from a memory aid standpoint, very easy to think about it in this way. Because as I've told you before, in delocalization, these bonds, when these electrons are delocalized, become stronger. They in fact become 1.5 times stronger than a single bond's strength. So they are 1.5 times the strength of a single bond. And I'm just gonna, this box with a line in it represents the strength of a single bond. And so they are, yes, 1.5 times stronger. And if we count these bonds out, we would have 1 bond here and half a bond there. That is 1.5 times the single bond. And this is very intuitive in the sense that it makes sense of the observations, the facts that I've given you regarding delocalization. But now, as we know, as we've always fallen back on, there is no more energetically stable state, because as we know, there can't really, this splitting of this orbital can't really happen. It's not something that can really occur. But what can happen is that these electrons can pool together, and as I've said so many times, they can pool together and form this superposition where these electrons are between the 2 extreme states of being completely double bonded here or completely double bonded here. And what this creates is the idea of the delocalization. And now I'm erasing the delocalization. And actually, if we look at delocalization, let's redraw this. Let's redraw this, and so we know, if we now draw out the valence energy level, hold on for a second, the valence energy level of the triangle oxygens, we've got our 1 electron in our 2s, and then our, if we're just looking at the promoted, the 2p, we've got our 1, 2, 1, 2, and 1. Okay, and so we know that this one is bonded, this one is not bonded, and then these 2 are lone pairs. Here, 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 here. Okay, and so now we have the problem of this single electron again. This single electron, and this is times 2. This single electron is a problem times 2. And that is kind of a funny way of putting it, but problem times 2. And now what we actually look at here is now we've got these 2 electrons that we don't know where to put these last 2 electrons. We know that this one for the star, this is the star, is the lone pair that we see here, and the 2 bonds that we see here are this and this. And so what we are left with are 4 electrons that we have no idea what to do with. We really, as we've said about the splitting, we have no idea what to do with them. We have no idea what to do with them. And so what we do is that's where we stick the 4 electrons right here in an in-between state of superposition. And really what we call these superposition electrons, and this is super important, we call these superposition electrons, they are in what we would call, they are in atomic orbitals. They are actually non-hybridized, and I will explain how I know in a second, even though for a while here I've been assuming they are hybridized. But they are non-hybridized, and they are therefore sitting in the potential for pi bonds. So they are sitting in what we call pi orbitals. Pi orbitals, which are essentially atomic orbitals in a bonded structure. So we can extrapolate this, and we can call them pi electrons. Pi electrons. And what we can say here is that they are delocalized pi electrons. So DL pi electrons. Pi electrons. And you get the picture now. Okay. So this has been an extremely long example. I'm sure I'm about 20 minutes now. Okay, so now I will give you the benzene example, and I will save NO2 for another day. And I will actually erase all of this. We ran out of room in the last example. So much chemistry. Just boggles the mind. Okay. I've become a whiz at erasing this. Go to the Olympics or something. Okay. Alright, ooh, shoot, I am almost messing up my board. Okay, so, and I will erase this as well. We know this video is about delocalization by now. Okay, so, we know now that the bonded and non-bonded pairs, bonded pairs and non-bonded pairs, plus NB pairs are hybrid orbitals, and the bonded pairs are sigma bonds. They are sigma bonds. They bond head-on. Whereas the double bonds, the single, and these are single bonded pairs. I am just getting ahead of myself. These are single bonded. Single. But then once we get into double bonds, double dash triple, so essentially more than just a single bond, we are getting into pi. We are getting into pi bonds. Shoot, not sigma, pi. And then as well, we've added to the pi bonds at least, or the pi electrons, we are calling the delocalization. Also part of this idea of atomic orbitals blending. The sideways on blending of atomic orbitals. And so in the last molecule, because I just forgot to mention this, I am not on top of my game as usual. We'll always make that excuse. These delocalized electrons do not affect the molecular geometry. Here we have the bent trigonal planar. And so, associated with this bent trigonal planar geometry is the bond angle of, for sure, less than 120 degrees. And this is true. This molecule has the same bond angle as any other bent trigonal planar molecule, regardless or in spite of the delocalized electrons. And this fact means that these delocalized electrons do not represent an influence in the molecular geometry, which means that they cannot possibly be hybridized. Non-hybridized. Which means that they must be pi. They must be atomic orbitals, or pi electrons as we call them. pi electrons. So that is perfect, and I just wanted to clarify that because this is all about understanding, and I want to make sure that we all get it. Okay. So now on to benzene, and I'm sure I've wasted 5 more minutes by now. And this is going to be another long one, but we can't have understanding if we don't have long videos sometimes. Okay, so the benzene molecule. The benzene molecule. And this is a extremely famous because it really brought about the idea of delocalization. But more importantly, it is an extremely important molecule. We're using important a lot because it just keeps coming up over and over again in organic chemistry, and it is called benzene. Benzene, just like Ben, and then we put some zine on top of it. Okay, so benzene. And so we take these 6 carbons, 6 hydrogens, and we connect them just like we're taught in organic chemistry. We connect them in a cyclic manner. Because we would call this is a cyclic molecule. Cyclic molecule where the carbons are connected. There's no end. They are simply connected in a sort of shape. And since here this would be a hexagonal shape, and then this, it makes perfect sense that therefore these carbons would be, because there's 6 carbons, must be bonded to, each have 1 hydrogen bonded to it. And we are all following so far. This makes sense. And now we will examine the hybridization of these carbons as usual. Because as we know, this molecule needs to have, so there are 4 valence electrons in the carbon. 6 times 4 is 24, and then 6 electrons in the hydrogens. There are 30 electrons in this molecule. 30 electrons within the molecule. So now how many do we have here without even writing out the hybridization? We've got our single bonds with the carbon. So we got our 2, 2, 2, 2, 2, that's 12. And then if we do that again with the hydrogens, we got 6 CH bonds. That represents 6 times 2, that's 12. So 12 electrons times plus 12 electrons. We've got 24 in this diagram right here. So where do the other 6 electrons go? How does this molecule bond? And this boggled scientists for such a long time. It was a big problem, and actually I'm confident, if I know my history right, the guy who solved this problem studied it so hard that someone came to in a dream and told him how this thing comes together, and he was very happy. He was happy. But don't expect that to happen to you. That's not how life works. You gotta work hard. I'm sure he did. He just got a bit lucky with those dreams, you know. They're quite silly. Okay, so how does these carbons hybridize with each other? So we've got our, let's just actually draw out the hybridization, or at least let's draw out the molecular geometry once the electron promotion has occurred, because just because electron promotion has occurred does not mean that all of these orbitals here, all p orbitals, will participate in being hybrid orbitals in determining the molecular geometry around a central atom. So we are looking at any central atoms, any central carbon around here. We are seeing right away in these bonds, these are all sigma bonds, they are all single bonds, and there are 3 of them. That would suggest sp2 hybridization. sp2 hybridization. So we've got our sp2 hybridization. The new orbital would look like this, sp2. And that is hybrid. And each hybrid orbital would have a half filled with electrons, and so it can bond 3 times. And that is, as we've seen here, very accurate. That is making sense so far. But then where does this extra electron go? It still single atomic orbital. Where does this extra electron go? Well, so the idea is that each carbon has this extra electron sitting here. They each have an extra electron sitting here. If we just visualize this in a sense for a second, that there are electrons sitting there. And they can bond this way with this one, or this way with this one. This one can bond this way with that one, or this way with that one. And this one can bond this way with this one, or this way with this one. And so we're really starting to see here how these arrows are going to start going back and forth. And this way with this one, and then this way with this one. And then this one can bond this way with this one, and then this way with this one. And then this electron can bond here and here. And so each additional electron sitting in this atomic orbital, not influencing molecular geometry, each one of these can bond with two other electrons to make stable states. But the problem is that each of these electrons belong to other carbons, which means that, there is no more energetically favorable state. The delta En is not different. No more energetically favorable state. They have the same delta En. Same delta En. Excellent. Perfect. So now we have this situation where they are essentially, again, in this idea where do I go? Do I go here? Do I go here? And this actually would end up working out very nicely if we go up here, just for a side note, and we were just drawing out the carbons. Let's forget the hydrogens for a second, because they don't really influence this idea anymore. We could get a state where the carbons are bonded like this, or where they are bonded, if I draw out benzene again, or where they are bonded like this. And so this really is the trademark of the superposition case, and this only seems to add to the evidence when we look at our hybridization that this electron, this extra electron, is a pi. It is an atomic orbital, which means it is a pi electron. So if there's no more energetically favorable state, what ends up happening is we end up with a delocalization over all 6 carbons. That is astronomical. That is groundbreaking. All 6 carbons. And maybe in a later video I will describe some of the evidence besides just simply bonding theories that led them to question the structure of benzene. But for right now, let's just stick this as the idea that there are 6 pi electrons within this cloud of electrons, in this probability cloud of electrons, where they could possibly be. And this makes all of these bonds stronger. In fact, all of these carbon bonds are made stronger, and I'm confident I'm going to try to say this, that they are 1, and we are going to say they are 1, and I think actually they are 1 1/2. They are indeed 1.5 times the normal carbon-carbon bond. And that is how much stronger they are. And the reason why I'm saying this is because there are only two states of this. There are only 2 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 sta possibility where the electrons could exist. These two extreme states, there are only two extreme states, so therefore we add a 1/2 to the single bond. I could be wrong, it could be a 1/6, but that is never going to be a question you're going to be asked on a test, at least not in high school. So do not worry, I do not know either. So that is essentially how delocalization is applied to molecules using hybridization as a proof of what we know here. We use the hybridization knowing what the molecular geometry is when we draw out our sketch of the Lewis structure. And so we know which electrons are hybridized, and then from there we work with the electrons that aren't to create a delocalization over the atoms that could possibly be bonded in one extreme state or the other. Alright guys, so I'm just gonna wrap it up for the night. You will see me very soon, hopefully, before I leave for my university outing. And I will talk to you one more time about a very special case in bonding. And then when I come back for Christmas, I will talk to you more about all this other stuff. I'm going to talk to you about intermolecular force, all that awesome, cool science stuff. So thanks for sticking with me all the way. Go watch all the other videos and study hard. Good luck, everyone.